Okay, so this last little bit, we're going to talk about kind of ad nauseum as we move through all of our reactions. But they do give you like kind of a, hey, these are the basic mechanistic steps that we're going to see throughout the next multiple chapters, okay? All right, so arrow pushing. I've already mentioned it, when we draw these little arrows and we are trying to represent electrons. Where have we seen this before? We've talked about arrow pushing before. Resonance was one, right? So with respect to resonance, was arrow pushing actually trying to represent the flow of electrons? No, right? So with resonance, we use arrow pushing, but again, it was just trying to help us find various resonance structures, okay? We've also used it in one other place where it actually did represent the flow of electrons, the movement of electrons. What other reaction have we already talked about in terms of arrow pushing?
Is it homolytic and bonds?
We talked about it, yes, at the very beginning of this chapter, but...
Last course?
Yeah, last course.
Oh.
So acid-base reactions, right? So we did start talking about arrow pushing and acid-base reactions. Unfortunately, no one remembers. So again, one of the steps that we'll talk about is that proton transfer step. So, okay, so I'm not going to really make an argument about why this is important. All I'm going to say is the fact that in the next few chapters, giving you kind of an idea of what's coming, we're going to go over quite a few different reactions, right? And in all of those reactions, you're going to need to know a bunch of stuff. So you're going to need to know types of reagents involved. You're going to need to know the types of products that are going to form. You have to consider stereochemistry, regiochemistry, etc. Okay? So the entire purpose of this is all of those reactions essentially can be broken down into these 4 basic mechanistic steps. So if you have a good handle on this, it's going to help you as we move along in our synthesis type chapters, okay? Okay, so we're going to use arrow pushing in our mechanisms and drawing our mechanisms for all of these basic steps. All right, so the first one that we're going to talk about is what we call nucleophilic attack, okay? So nucleophilic attack, who do you think that involves? So why have we identified what these things are before we've even talked about this step? So who do you think a nucleophilic attack involves? What type of species? A nucleophile, right? Okay, so again, a nucleophile is an electron-rich species, okay? In this arrow-pushing pattern, the electrons of that nucleophile are going to go and they're going to attack an electrophile, okay? So we have our negatively charged electron-rich nucleophile. The electrons of that nucleophile are going to go out and they're going to attack an electron-deficient center or an electrophile, okay? Those electrons are forming a bond, right? So we're taking those 2 lone pairs of electrons, or that one lone pair of electron, we're forming a bond. Our resulting product is that nucleophile attached to the electrophilic center. Okay, so again, electron. The arrow starts at the electrons that are going towards the thing that they're actually going to be forming a bond with. So the head is always pointing towards our electrophilic center as clearly as we can possibly show it. Okay, so this can occur in one step, which is what we showed here, where we had our nice bromide attacking our carbocation. This could also require multiple steps, right? So for example, let's say that we had our alcohol down here. We had our nucleophile. It's attacking our electrophile, right? So we have our partially positive carbon right here, our nice electrophilic center, okay? If I go ahead and I take those electrons and I attack that carbon and I don't do anything else making a bond with that carbon, what's the problem here? So if that resulted in our nice little molecule here, what's the problem with that carbon at this point in time? It has 5 bonds. 1, 2, 3, 4, 5, right? So sometimes we'll have to accompany this with more than one arrow, right? So if this guy's being attacked here by our nice little nucleophile, then we're going to break that pi bond and those electrons are going to go up to our oxygen. Right? So then we end up with our product where we have a single bond, and we have a single bond, and we're not breaking carbon's octet rule. Okay, nucleophilic attack. Where does the arrow start? The nucleophile or the electrophile?
Nucleophile.
Where specifically on the nucleophile does it start?
Here, Bob.
Lone pair of electrons, right? Electrons, where are they going to? Where does the head of the arrow end up?
In the charged carbon or the one with
The electrophile, the electrophilic center. It's always the electrophilic center, right? Depending on what that center is, depends on if we need more than one arrow. But again, first arrow, starting at the nucleophile, going to the electrophile. Okay, so that's pattern 1. There's only 4, right? So that's it. It's 1/4 of it done. Next pattern is also really easy, right? So it's called loss of leaving group, okay? What do you think is going to happen in this mechanistic step it's called loss of leaving group? What do you think is going to occur?
again, break a bond.
Something's leaving, right? Something's going to break a bond and something's going to actually leave the molecule, okay? So for example, here we have our nice alkyl halide, okay? In this loss of leaving group step, this bromine is going to take the electrons in that bond and it's going to take them with it, okay? So now this bond is gone in our products. What's the problem with that carbon if all these electrons go with bromine?
There's a charge.
So it had 8, right? It had 4 bonds around it. If these electrons are now gone, it now only has 3 bonds around it, right? So we're forming what? Carbocation, and those electrons are now going to show up as a lone pair on our leaving group. Okay, so this guy is called a leaving group. And again, in loss of leaving group, it's leaving, and it's taking electrons with it.
Wait, the leaving group is one thing?
The leaving group is one thing, yeah.
All right.
It is that bromine. Bromine left. It is the leaving group. So, in loss of leaving group, where does the arrow initiate?
The bond that's broken.
The bond that breaks, right? And that bond is specifically attached to who?
The C, the carbon will be R.
Or the thing that
The group is leaving.
leaves, right? So in loss of leaving group, the arrow starts at the bond that the leaving group is attached to. Who does it go towards? The leaving group, right? Because it's taking those electrons with it, okay? I know. I'm really trying to stress this because arrow pushing people really struggle with, so.
You're getting really pushy.
What?
You're getting
Really
really pushy.
pushy, yes.
What did you write over here on top of the
LG. I will abbreviate leaving group a lot as LG.
Okay, leaving group.
Leaving group. Here, we'll do a equals leaving
Fancy.
group. I know. Well, I get my, it's better than I change my G sometimes. Okay, all right. So that's easy, right? Loss of leaving group. Something leaves, it takes electrons with it. That's 2. There's only 2 more, okay? The third one we've already seen. It's a proton transfer reaction. Okay, so a proton transfer reaction, instead of having a nucleophile or an electrophile, we're instead going to have an acid and a base. What do acids do? Donate protons, right? What do bases do? Receive them, accept protons. How do we draw that mechanistically, though? Because this is kind of the reverse. We always talk about proton donation. But in reality, the base goes out and gets the proton, right? And it's the electrons of the base, that lone pair of electrons, that goes out and abstracts a proton, okay? So in proton transfer, we have the base getting that proton, making a bond with it. If this oxygen does that to this hydrogen, how many bonds would hydrogen end up with if nothing else happened?
2.
2. Is that possible?
No.
No, right? So always in a proton transfer step, you've got the electrons of the base going to make a bond with the hydrogen, but these electrons that are in the acid have to be left behind on what is going to become the conjugate base, right? So we have 2 separate steps. We have the proton, or the electrons, going to get the protons, and then these electrons that are in this bond being left behind. And again, if this is our base, and this is our acid, and this is our conjugate acid, and then water, would be our conjugate base.
Did they not draw the water because it's implied? Or
Yeah, it's implied a lot of times.
Oh. Okay.
Okay, so that's the easy three. Oh, no, 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 no. Yes,
On the base of the lone pairs, it goes straight to the hydrogen, right? Not to the bond of the hydrogen.
it goes straight, so the electrons of the base go to take the hydrogen, so it goes straight to the hydrogen, and then the other ones stay on. Hold on just 1 second. Oh, man. I know, it's great. I'm glad that you're trying to learn.
Does it show
Why
up
I
after the
oughta. I think it must. I think it's been on since 8, so. Oh, whew. Okay, so I'm only going to briefly start to introduce this next one, right? So we had nucleophilic attack, we had loss of leaving group, we had proton transfer, right? The last step is a little bit more complicated, and people tend to struggle with it a little bit more. And it's actually going to talk about, or go back to, this idea of a carbocation, right? Because we're going to have, this last step is called carbocation rearrangement. Okay, so carbocations. Let's talk about them very briefly, okay? So in a carbocation, we have a carbon. How many bonds does it have to it? Only 3, right? How many lone pairs of electrons does it have around it? 0, right? So what is the molecular geometry of a carbocation? So 3 things, getting as far away from one another as possible, right? So this guy is trigonal planar. Trigonal planar. Most importantly, what type of hybrid orbitals does that carbon use in making that trigonal planar geometry? sp2, right? So if it's sp2, then what do we have left in terms of atomic orbitals that aren't really participating in anything right now? We have, because we have an s and 2 p's already taken up, but how many p's do we always have as in terms of atomic orbitals? 3, right? So we have 1 empty p orbital that isn't participating in any type of bonding at this point in time. Okay, now, what we find with respect to carbocations is the more alkyl groups that we attach to a carbocation, the more stable that carbocation is, okay? And what I mean by our alkyl groups, so we always represent this as R, so this is alkyl, if you're British, alkyl. What do I mean by that, alkyl or alkyl? What are these always usually? Just carbon hydrogen chains, right? So it can be carbon CH2, CH3, whatever. We're just looking at carbon attached to that carbocation, okay? The more of those alkyl chains that are attached to that carbocation, the more stable that carbocation is, okay? And we define these guys via how many groups are actually attached. So, for example, if we have a carbocation where all we have attached to it is hydrogen, and we don't have any alkyl groups, we call that a methyl carbocation, okay? If we instead substitute that with 1 alkyl group, we call that a primary carbocation, and we represent that as a 1 with a little degree sign up top, okay? So primary, when you see this 1 with a degree sign, that's referring to a primary carbocation. So as we increase the degree of substitution, so if we replace it with 2 alkyl groups, we call that a secondary, and again, it's going to be a 2 with a little degree sign. And if we end up with 3, we call that a tertiary carbocation. We call that a 3 with a little degree sign. Okay, so the more alkyl groups attached to this carbocation, the more stable it is. Why is that? So again, it goes back to this empty p orbital, okay? And in this empty p orbital, if we do have this nice alkyl group attached to it, what type of hybrid orbitals would this carbon be using if it has 4 bonds to it, super happy tetrahedral? So these would be sp3 hybrid orbitals. These would all be bonding hybrid orbitals. What we find is that there is electron donation into that empty p orbital of the carbocation, right? So we have an alkyl group that's attached to it. Those bonding molecular orbitals actually are allowed to donate electron density into that empty p orbital, okay? Anytime we're allowed to donate electron density, it's kind of like resonance, right? If we can spread out electrons, it's going to be more stable overall. So the more groups that are attached to that carbocation with that empty p orbital, the more electron donation from those bonding MOs we get, the more stable that overall molecule. Okay, because again, we always want to spread out electron density, and that's what happens when we attach alkyl groups to it. Okay, this process we'll come back to because it has other manifestations. This process is called hyperconjugation. And again, it's this electron donation from these attached alkyl groups from their bonding molecular orbitals into that empty p orbital. Okay?
So the empty has a slightly positive charge then?
The empty has a slightly negative charge, or it's like, it's positive,
Right.
like the center is positive, but now that we're allowing the electron donation into it, it's stabilizing that positive charge. Because again, carbon doesn't like to have less than 8 electrons. It has it now. The more electrons we can put in it, the happier it's going to be, to make it not as positive.
Where is it getting the electrons from?
It's getting it, so again, this is our carbocation.
Okay.
This is this empty p orbital.
Okay.
This guy is a bonding molecular orbital from a carbon right next to it.
Okay.
So those electrons are allowed to donate into that empty p orbital. And the more that you have around it, right now these guys are just hydrogens. If this instead was another carbon, the more electrons we'd be able to donate into that empty p orbital. Yes.
Why is the other carbon positive? Like, have a positive.
Because it's an alkyl group, right? So this is literally a CH2 with another bond going off. It's not a carbocation.
Oh.
It is a normal tetrahedral sp3 hybridized carbon. It's only the things that are surrounding this carbocation that has this empty p orbital. Hydrogen can't do that, right? Hydrogen can't donate any electron density into that p orbital. So because of that, these are really unstable, but these are really, really, really stable. Okay, so who is the most stable carbocation? What would you say?
Tertiary.
Tertiary, okay? So the end of this story is things are going to happen to make sure that we have a tertiary carbocation. So things are actually going to rearrange in the molecule so that we can ensure that we have the most stable carbocation. But how can they do that, really? What can they do to ensure that they are the most stable carbocation? So what we will find is if we have a carbocation, right, and it is allowed to do what we call carbocation rearrangement to form a more stable carbocation, it will do that, okay? So for example, let's say that we have this carbocation right here. What degree of substitution do we have about this carbocation right now? Is this a primary, is it a secondary, tertiary carbocation? How many other alkyl groups do we have branched off?
2 more.
2 more, right? So it's a secondary carbocation, right? So number 1, we have a secondary carbocation here, okay? Now, the positive charge is at this carbon, right? But what we're going to do is we're going to look to the 2 adjacent carbons, okay? So in these 2 adjacent carbons, what we can see is if we have a hydrogen in an adjacent carbon, what we can see is something called a hydride shift. So for a hydride shift, what we're actually going to look at is hydrogen with the electrons in that bond actually shifting and filling that hole. Okay, so the arrow pushing here would be the electrons that are in this bond going to fill our little positive charge carbocation. Okay, so this guy, this whole hydrogen, essentially just moves over. We no longer have the positive charge at that carbon, instead it moves to the carbon where that hydride came from. Okay, when it does that, what type of carbocation do we have now?
Is it a loss of a group because you lose an H?
We don't lose anything. The hydrogen actually shifts over. It was here, it had a bond to this carbon, that hydrogen is now moved to this carbon. So we're not losing anything. But what type of carbocation have we made in that hydride shift?
Proton transfer?
This guy. How many different alkyl groups are around our new carbocation?
1, 2, 3.
3, right? So who's more stable, a tertiary or a secondary carbocation? Tertiary, right? So you will see this occur if via this hydride shift you can form a more stable carbocation. Yes?
Alright, I was just wondering, how do you determine how that one is tertiary again? So is it because at that carbocation, there's, like, it goes to 3 different carbons
Yes.
instead of,
Yes. So here, this guy only went to 2 different carbons, and it went to a hydrogen that's implied.
Mhm.
Here, now we have this guy going to 1, 2, 3 different carbons. This is our tertiary carbocation.
So in this type of group, sorry, it's the, you said group 4, the carbocation rearrangement.
Mhm.
That's only when the molecule is itself, right? There's
Yeah.
no other additions.
No other addition. It's literally rearranging internally with itself. Okay, so again, that is a hydride shift. Okay, and again, we're looking at if we can form a more stable carbocation, we will via shifting of a hydrogen. We can also see something that's called a methyl shift, right? So in a methyl shift, again, we go from a secondary carbocation in our reactants. Instead of this being a hydrogen now, we have an entire methyl group shifting over to fill that hole. So again, it's the electrons that are in this bond going to make a bond with what was our carbocation. So now this guy has a 0 formal charge, it's happy, it's good, but that positive charge is shifted to this carbon where that methyl group came from. So again, what type of carbocation have we formed in this process? Tertiary, okay? So these are the only 2 ways that we can see any type of carbocation rearrangement, a methyl shift or a hydride shift.
So the arrow just goes wherever the positive.
Wherever the positive's going. And the positive goes to wherever that thing was coming from.
Okay.
It's kind of like if you want to imagine this filling a hole, you fill a hole here, but you essentially make a hole over here. Okay, so then the question is, well, how do we know? How do we know whether or not something is going to rearrange? So for example, let's say we had a molecule like this, right, where we have our carbocation at this carbon. How do I know, number 1, is there going to be a rearrangement? And number 2, what's going to be the product of that rearrangement? So first off, let's start by saying, okay, what type of carbocation do we start with? What type with respect to substitution?
A second degree.
So this is a secondary carbocation, right? And again, the only time I'm going to see shifts or rearrangements is from positions that are directly adjacent to it, okay? So when I'm looking at this, I'm focusing on this guy, my directly adjacent carbon, and this guy, okay? Now, I have to imagine what's going to happen if I see shifts from either of those 2, okay? So at this carbon right now, this guy, what is there that could shift? Do we have a methyl group? It has to be a methyl. It can't be like an isopropyl or anything like that. There's no methyl group there, but what about hydrogen?
Yeah.
Yes, so we have 2 hydrogens here, right? And regardless of which one shifts, we're going to get the same product, okay? Where else should I look at with respect to these shifts?
The right side.
The right side, right? So we have this guy. Is there a methyl group there?
Yes.
Yes, so we have a methyl group. We could potentially see a methyl shift. What about a hydride? Could we see a hydride shift from this position as well?
Yeah.
Yes, so there is an implied hydrogen. Again, remember the implied hydrogens, okay? So what we have to look at is what happens if all of these 3 things shift. What is the possible products? So if I start over here with these guys first, and I say, okay, let's say that I'm going to see a hydride shift to this guy. I'm going to go ahead and draw my product. So we have, God, that's pretty. 3 hills. We've got this guy, and now we have moved a hydrogen here, right? So we've filled that hole. The positive charge now goes to this guy. And it still has 1 hydrogen attached, okay? So we had a secondary carbocation initially. What have we made in that hydride shift? We've taken a hydrogen, we've shifted it over, so that's the new thing that we've created. But what is the new carbocation that we've made?
It's still a secondary.
It's still secondary, right? So if you see a shift and you form the same stability carbocation, you're not going to see that shift, right? It's going to stay where it is. So we can ignore this guy, okay? So this would be a no. Now, let's move to the other side, this guy, and look at the various products that we can get from either the methyl shift or the hydride shift, okay? So let's imagine that we have that methyl shifting first. So we'll have methyl shifting to form, or to plug that hole. So the outcome of this guy would be hills, valleys. We'd get the methyl at this position. We'd still have the hydrogen here, and the positive charge would move here. So now, what have we formed?
We went from second degree to third degree.
Is it tertiary? Again, our new positive charge is that this carbon, it's only attached to 1, 2, and a hydrogen, right? So this is, again, formation of a secondary carbocation. It's not any more stable than the original one, so you're not going to see this occur at all. Okay, so that was hydride shifts from here. We had a methyl shift from here. We're not going to get anything that's more stable. The last thing that we're going to look at is that other hydrogen, right? So if we move this guy and we see a hydride shift, the product of this is going to be, this is our new hydrogen, this is our new carbocation, this is our overall product.
That's tertiary.
Right. I wish I wouldn't have used blue. It's kind of limited. You know, it's like the black and the red are strong, but blue is not a very good color on this thing. It looks good on here, just doesn't look good up here.
Oh, no,
Now that one's more stable.
Right, because now we've shifted that hydrogen, we've filled that hole, so this is our new hydrogen-carbon bond. Now we've moved that positive charge over to that carbon. It is now tertiary, right? So this is a tertiary carbocation, which is more stable than our secondary reactant. So this is one that we're actually going to see. This will be the rearrangement. And if you were predicting the product, this would be the acceptable answer. Okay, so that's how you know, right? So you have to look at all of the various possible things that can shift. You have to check what type of product you're going to form. If you do form a more stable carbocation in your product, that's what you're actually going to see, okay? Now, for the most part, once we reach tertiary carbocations, there's really not going to be any more shifting that could lead to a more stable one. The only ones you have to watch out for is if you do have a tertiary and it can shift into an allylic carbocation, okay? So what do I mean by that? So for example, right now, this guy is a 1, 2, 3, a tertiary carbocation. You would think, oh, we can't do anything with this. But if we looked at this guy and said, what if we see a hydride shift? If we do that, the product that we're going to get with our new hydride, nope, with this guy with a positive charge, with this guy, is this more stable? It's tertiary again, which is great, but what else is there that we haven't really mentioned? A double bond, but more importantly, with respect to this positive charge being in an allylic position, what can we draw as a result of this?
Like a resonance?
Yeah,
resonance?
resonance structures, right? So with this guy, there is one resonance structure that we can draw. God, I can't draw today. I wish I was doing this on the board. So we draw our little resonance arrow. We get our double bond, this guy, we get this guy, and the positive charge moves over here, okay? So the purpose of this was tertiary. Usually you're not going to see a rearrangement. The only time you could possibly see a rearrangement if it's allowed to rearrange into something that has an allylic carbocation. Because again, that whole idea behind resonance, we're delocalizing charge, which is good, which is more stable. So this guy would form, because again, now it's allowed resonance, it's more stable, things are always going to tend towards a more stable situation. Will form.
So it starts off as tertiary, then why does it change resonance?
Because by undergoing this rearrangement, it's allowed that positive charges to move. Now we have an allylic carbocation, right, which has a resonance structure. The more resonance structures you have, the more stable you are.
Even if that's a lower.
Yes.
Okay.
Yeah. So again, the purpose of this little diatribe is that most of the time, tertiary, we don't care about, we don't even have to look at, except for the times where it could rearrange into an allylic carbocation. Okay. Okay, so hydride shift, methyl shift. let's go ahead and get some practice with those two and predicting whether or not a carbocation will rearrange and then what the product would be after rearrangement. So I have two carbocations and I want to know, number one, will they rearrange? What type of rearrangement are we seeing? And then what's the product after rearrangement? And so again, with the majority of these, if you guys want to give it a shot, pause the video and then come back for the answer. But I'm going to go ahead and go over these, or the answers to these now. Okay, so first off, we're going to look at our starting material. So we have an A up here. We have a B down here. So these two different problems. I'm trying to determine, number one, do I expect to see rearrangement? And if there is rearrangement, what is the product overall? Okay, so we're going to start with A. At A, we're looking for that carbocation, that positive charge on a carbon. And we're determining what the substitution is about that carbocation, right? So right now, I note that there is the carbon that we're looking at is attached to one other carbon, another carbon. There is a hydrogen here that's implied right now, right? So we do have a hydrogen up here, but because it's only attached to two other carbons, this is what we would determine as a secondary carbocation, okay? Now, we're looking for whether or not we're going to see rearrangement, and we will see rearrangement if this can somehow rearrange into a more stable carbocation. Specifically, above a secondary carbocation would be a tertiary carbocation. Okay, so that's what we're looking at. Is going to be able to rearrange via either a methyl shift or a hydride shift to form that tertiary carbocation. So the first thing I'm going to do is I'm going to start at this carbon. Right, because again, when we're looking for a rearrangement, we're only looking for the adjacent carbons to the carbocation. At that carbon, we have two hydrides. There are no methyls. And so let's say that one of them actually did shift, right? So we do see, let's say that that's what we saw. So we would go up here. We would draw our product. We have this guy, methyl. We've got a new hydrogen bond here, but again, essentially the same overall structure. We still have a hydrogen here, but now that positive charge has moved to this carbon. Let me actually make that a little clearer. Oops, that's gonna be dizzying. Now that positive charge has moved to this carbon, okay? So, in going from this guy to this guy, we've gone from a secondary to, hopefully you should be able to see that this is also a secondary carbocation, right? We only have attachment here from this guy, right? So there's only two carbons attached to the carbocation. It's a secondary carbocation. So because of that, because we go from secondary to secondary, this is not going to be something that we see, right? We're only looking for the production of a more stable carbocation. Okay, so we can go ahead because of that and cross this carbon out. Now, if we look over at this carbon and things that are attached, there are no hydrogens attached, so we're not going to see a hydride shift here, but we could potentially see a methyl shift, right? So let's say that we had a methyl shift to that carbocation, and so then we'll go ahead and predict the products for it. Forgive me for I haven't drawn in a while. So now that's a methyl group. We still have a methyl group left at that carbon originally, and now the positive charge has moved here, okay? So we've gone from a tertiary or secondary carbocation to now, ideally, you should be able to see that this is a tertiary carbocation, okay? Tertiary is more stable, so the answer to this is yes, we do see a shift, and specifically we see a methyl shift, and this would be our product, right? There's only one way to really rearrange this that produces a more stable carbocation. It's via that methyl shift from this carbon, and the resulting product is given there. So hopefully you guys got that. If we get on below here, same thing. We're looking at our carbocation here. Right now, it is a secondary, pardon me, it is a secondary carbocation. There's only two places that we could look for rearrangement from, right? So we could look from this carbon that's directly adjacent to it, or this carbon that's directly adjacent to it. if we start at the right carbon, so let's say we start out here, we essentially at this carbon have 3 hydrogens that are implied. So the only thing we can expect to see from shifting from this carbon would be a hydrogen via hydride shift. So let's say that happened. We go ahead and draw our resulting product. So again, we have a new hydrogen bond there. The whole or the positive charge moves to this carbon, and now unfortunately we've taken something that's a secondary carbocation and we have made a primary carbocation, right? There's only one carbon, or let me go to my highlighter, one carbon directly adjacent to our carbocation, so this is a primary carbocation, which is actually less stable than what we initially started with. So because of that, we will not expect this guy. So we can ignore the remainder of the guys or the hydrogens on the right side because they're going to produce the same thing. If we instead go over to this carbon, we have a couple of things that can happen. We have methyls, right? So we have methyl 1, methyl 2. We also have an implied hydrogen here. So let's say that one of the methyls shifted, right? So let's say that we had this guy come over, fill that hole, and we can draw the potential product from it. So for this guy, that may be confusing. Let me do this. That's really ugly. Okay, 1, 2, 3, right? So now we have a methyl group here, just shifted to fill that hole. It was like what was here, right? That positive charge has now moved to this carbon. And again, we still have a hydrogen here. So we had a tertiary, or a secondary, secondary carbocation that has in this methyl shift, and we'll go ahead and write that, methyl shift. In this methyl shift that has formed a secondary carbocation, right? So again, we're not looking to form things with similar stabilities. We're looking to form things that are more stable. So this will not occur. But there is one other option. I'm going to go to red for this. So we still had this hydrogen, right? So we looked at what happens if the methyl shifts from that carbon. What happens instead of the hydrogen shifts? We have a hydride shift from that carbon. So for this guy, this is our hydride shift. If we draw the resulting product from this one, we have a new carbon-hydrogen bond here. That's what's shifted. But we still have both methyls at that carbon, right? And so the positive charge has now moved to that carbon. And now we have formed a tertiary carbocation, right? Because again, if we look at what's surrounding this guy, it is this guy, and this guy. That is a tertiary carbocation. So we do expect to see a shift. So the answer here again is yes. The only viable shift is this hydride shift from, let's say we call this guy 1, 2, 3, 4. So a hydride shift from carbon 2. And our resultant product would be this guy. So hopefully that was clear on how to predict whether or not we expect to see rearrangement and whether or not, or what the actual product would be that we expect to see.